Ever wondered how AI learns to adapt to new situations? Like how a robot trained in a lab can suddenly handle a wobbly table or a changing floor texture. That's the big challenge in reinforcement learning, making agents generalize beyond their training. But what if we could teach them to guess how to handle new environments, even if they've never seen them before? Today, we're diving into a groundbreaking approach that's changing how AI learns from few examples. Let's start with the basics. Reinforcement learning is like training a dog with treats. The agent, the dog, tries actions, gets rewards treats, and learns to maximize them. But here's the catch. Most AI models struggle when the real world doesn't match their training. Imagine a robot that's mastered walking on a smooth gym floor, but freezes when faced with a muddy backyard. Why? Because it's never seen that context, the hidden variables like friction, gravity, or terrain texture. This is the problem the researchers tackled. They call these hidden variables context parameters. Think of them as the rules of the game that change between environments. Traditional methods force agents to train on dozens of these contexts, which is time-consuming and impractical. But what if we could make an agent generalize from just one? That's where their new idea, the Context-Enhanced Bellman Equation, CEBE, comes in. So what's a Bellman equation? It's the mathematical heart of reinforcement learning, helping agents predict future rewards. The CEBE tweaks this formula to account for context. Imagine you're learning to drive in a city with specific traffic rules. The CEBE lets the AI say, okay, I know the rules here, but what if the speed limits change? Let me estimate how my actions would work in similar scenarios. It's like having a map that helps you navigate new roads based on the ones you've already studied. But how do you test this? The team developed Context Sample Enhancement, CSE, a clever way to generate fake data from a single training context. Think of it as tweaking a simulation. If your robot learns on a flat surface, CSE might pretend the floor is slightly tilted or slippery, teaching the robot to adapt without ever seeing those conditions in real life. The results? In experiments, agents using CSE outperformed traditional methods by a mile. They handled tricky scenarios like sudden changes in gravity or reward structures, all while using far less data. It's like giving a chef a single recipe, but teaching them to tweak it for any ingredient swap. So why does this matter? Imagine training a self-driving car in a simulator. With CSE, it could learn to handle unexpected road conditions, like a sudden snowstorm or a detour, without needing to simulate every possible scenario. That's zero-shot generalization, learning to adapt without explicit training. Of course, there's a catch. CSE works best in smooth, deterministic environments. Real-world systems are messier, with random noise and partial information. But the researchers are already exploring ways to tweak CSE for these challenges, like focusing on the most sensitive parts of the environment or using adversarial perturbations to stress test the AI. Now let's shift gears to a related but distinct problem: how AI balances multiple goals in complex environments. Think of a robot navigating a maze while avoiding traps and conserving energy. This is where Constrained Markov Decision Processes, CMDPs, come in. CMDPs are like supercharged versions of classic AI problems, where the agent must optimize not just one objective but several, often conflicting ones. How do researchers tackle this? They use bi-level optimization. Imagine solving two puzzles at once. The first puzzle is the big-picture strategy. What's the best way to reach the goal? The second is the fine-tuned details. Should I turn left or right here? By optimizing both layers simultaneously, the AI becomes more efficient and adaptable. But here's the challenge. Real-world environments are messy. Think of a robot trying to walk on uneven ground, or an AI playing a video game with random level designs. These situations aren't always differentiable, meaning the AI can't easily track how small changes affect outcomes. That's where stochastic hypergradients come in, mathematical tools that help the AI adjust its strategy even when the rules are unclear. It's like giving the AI a built-in, trial-and-error, cheat code that learns as it goes. To keep things stable, the team used Lipschitz continuity, a concept that ensures small changes in input don't lead to drastic, unpredictable outputs. Picture a function as a hill. If the hill is steep, a tiny nudge could send the AI tumbling. But with Lipschitz continuity, the AI knows the hill isn't too steep, so it can make safe, predictable moves. They also relied on stochastic hypergradients to handle uncertainty, allowing the AI to refine its strategy iteratively. The implications are huge. From autonomous vehicles to robotics, these advancements mean AI can now handle complex, real-world scenarios with fewer constraints and more adaptability. But the journey's far from over. Researchers are still refining these techniques to tackle the chaos of the real world. So what's next? The future of AI isn't just about learning faster. It's about learning smarter, with the ability to generalize, adapt, and thrive in environments we've never explicitly programmed. And that's the real magic of modern reinforcement learning.